Carbon-13 nuclear magnetic resonance spectroscopy, or Ch14 NMR, is a magnetic resonance technique that takes advantage of the flippability of carbon-13 nuclei spin states, which allow us to use magnets and radio pulses to study the carbon atoms in a molecule and the different types of environments they're in. Now, the key spectral features we're going to look for when we look at a Ch14 NMR spectra is going to be the number of signals and the chemical shift at which they appear. The number of signals will tell us that the number of different or non-equivalent carbons that are present in a compound, and the chemical shift is going to tell us something about the environment that they're in and the type of carbon they are. And the chemical shift is where on the x-axis each signal appears. The chemical shift is primarily dependent on the hybridization state of each carbon atom and whether or not there are electronegative atoms or electron withdrawing groups nearby. We're going to look at 4 sample molecules in this discussion, which are the same 4 that we looked at with the infrared spectra. The chemical equivalency, or whether or not carbons will produce the same signal or different signals based on whether or not they're in the same environment, is a key concept of Ch14 NMR as well as hydrogen NMR. And remember that carbons are equivalent if they're in the same situation or environment, and they'll produce a single signal. If they're in different environments, they'll make different signals. So see if you can predict how many signals each of these molecules would produce in the Ch14 NMR. And remember that number of signals is going to be the number of sets of chemically distinct or non-equivalent carbons. So 2 or more carbons that are equivalent will produce the same signal. And we'll just run briefly through these. The ketone here will produce 3, the alcohol 2, the carboxylic acid 3, and the ester should produce a total of 6. Now we'll look at these in detail if you had trouble with this. If not, you can go ahead and move on to the next slide. In the ketone carbon itself is definitely going to be a unique signal because it's the only carbon that has an oxygen double bonded to it. The CH2s are both equivalent to each other, although different than the carbonyl, and they're the same as each other because of the symmetry of that ketone. They are both on either side of alpha to a carbonyl, and they're both attached also to a methyl group. And likewise, those 2 methyls are going to be equivalent to each other because they're each attached to a carbon with 2 hydrogens, a carbonyl, and an ethyl group. The alcohol carbon is going to be 1 signal in the alcohol, and the 2 methyls in this case are equivalent to each other, and so they will each produce a different signal. In the carboxylic acid, the carbonyl carbon will be 1 signal. The CH attached directly to it will be a 2nd signal, and then the 2 methyl groups are going to be equivalent because they're both attached to that CH. Finally, in the ester, we've got 1 carbonyl carbon that is unique. We have a methyl group that's unique, and it's the only sp3 hybridized carbon. And then looking at the ring, we have the carbon that bears the ester, the ipso carbon, if you will. We have the 2 carbons that are ortho or adjacent to the ester group. They're the same as each other, again, because we have a line of symmetry that passes through that ring and ester group. we have the 2 carbons that are meta to the ester, and then finally we have the carbon that's para to the ester. Now those may be very similar, but in theory at least they'll be chemically distinct. The other key feature of an C13 NMR spectra is going to be the chemical shift. And that's essentially where on the x-axis a signal appears. And these are some representative ranges. Now it's worth noting that that x-axis is usually in ppm, and for a C13 it typically runs from 0 to about 200, and that it runs backwards from what you might normally expect. So the numbers actually increase moving from right to left. Now if we think about dividing this spectra into 2 halves, right at 100, sp3 carbons are typically on the right hand side, sp2 carbons are typically on the left hand side. Now we don't see sp carbons a whole lot, but they will be in the upper end of the sp3 range. Now it's worth noting that there's some languaging that goes with NMR spectra. The higher chemical shift numbers are referred to as downfield or de-shielded, and lower chemical shift numbers are referred to that direction as upfield or shielded. And these can be relative terms too, so we might say, for example, that sp hybridized carbons are more de-shielded or downfield of sp3 carbons. Now it's also worth noting that when there is an electronegative element attached to a carbon, that it de-shields the carbon relative to where it would be without that element present. So that means that an sp3 carbon with a halogen on it, for example, or an oxygen is going to be downfield of most of typical sp3 hybridized carbons. Now that's true for sp2 hybridized carbons as well, and the most pronounced difference is going to be our carbonyls. So a carbon that's double bonded to an oxygen is typically going to be down, very far downfield. And so you could even consider that as a separate section of the NMR. So beyond around 160 to 180 are carbonyls, and then the regular sp2 carbons, either for alkenes or arenes, like a benzene ring, for example, are going to be in the moderate left-hand side of center, or between 100 and maybe with electronegative elements attached, maybe 160. So this is a handy chart to have, and there are other ways of representing this as well as in a table, but whatever you find, you might remember again, we're looking for essentially 3 separate regions. sp3 and sp2 separated by roughly around 100, and then way downfield on the left-hand side of the graph, we'd expect to see our carbonyls. Let's look at some examples. So here is a real C13 NMR of a molecule. We can identify it as a C13 NMR by the fact that we have ppm. That tells us it's an NMR, a C13 NMR, because those numbers run roughly 0 to 200. And in this case, notice that there are 2 features present. We'd say these are 2 signals. Right? And so just, it doesn't matter how tall they are or how wide they are, they're typically very sharp in the C13 NMR. What's important is simply at what chemical shift numbers they appear. And see, since these are both upfield of 100 ppm, we would assume they would be aliphatic, right? So this is in the sp3 range. So do you remember which of these four molecules would produce only two signals in the NMR? It should be isopropanol, that has one carbon close to with the oxygen directly attached, and a second carbon that represents the two methyl groups, second carbon signal that is, representing the two methyl groups that's further removed from the oxygen. Now we could actually assign the signals in this NMR spectra to those two carbons, knowing that the de-shielding effect of the oxygen as an electron withdrawing group or an electronegative element is going to pull the signal for the carbon directly attached to it downfield relative to that of the CH3 group or CH3 groups. And that effective electronegativity, de-shielding elements, tapers off quickly with distance. So the two methyl groups feel it a little bit, but not nearly as much as the carbon to which the oxygen is directly attached. In this example, we can see that there are a bunch of signals, including one in the sp3 range and a total of 5 in the sp2 range. And one of them stands out from the others by rights of being very far downfield. That's likely to be a carbonyl. Notice there are, and we're even told, since they're close together it's hard to tell, there are 4 signals that are in the sp2 range that are clustered fairly close together. And although there are 3 other structures besides the alcohol that have carbonyls present, the only one that has this many signals, this is a total of 6, is going to be the ester. And so we can say that this spectra represents this compound here, and that we can assign the sp3 signal, that's going to be our CH3. We could write the CH3, or we can write letters A, B, C, or we can write shapes, however we want to express that. We put a triangle around the carbonyl carbon, of course, is going to be here. And then the 4 signals here are all going to be part of our ring. And we could imagine that the most de-shielded would be the carbon to which the electron withdrawing group, and remember that an ester is an electron withdrawing group. It's a meta deactivator and electrophilic aromatic substitution. For that reason, that carbon is going to be the carbon that's closest to it, although since they're all clustered pretty close together, it's difficult to say for sure which is which. Now the last 2 structures that we're looking at, the ketone and the carboxylic acid, actually have very similar Ch14 NMRs. So here's one of them, and here's the other one. Notice the differences are a subtle change in, or subtle difference in the carbonyl signal. This one is probably about 185. In the other spectra, the carbonyl appears downfield of 200, maybe about 215. And there are subtle differences as well in the chemical shifts of the aliphatic or sp3 hybridized signals. In this case, we've got one around 20 and the other one around 35. In the other example, they're more like 15 and maybe 38 ppm respectively. So at our level, either one of these molecules would fit those structures. As it happens, this one is the ketone, although we couldn't necessarily distinguish between the two at our level. So we're just going to take for granted we know this is in fact the ketone, and from there, of course, we'd rationalize the carbonyl being the furthest downfield. We can guess or be reasonably sure that the carbons that are closer to the carbonyl will be more de-shielded than those for the methyl groups, which are further from the carbonyl. And that would be true for the carboxylic acid as well. So this NMR spectra corresponds to our carboxylic acid. The carbonyl is pretty distinct. The carbon closest to the carbonyl carbon we would expect would be somewhat downfield of the signal produced by the two methyl groups, which would be the least de-shielded or the furthest upfield.